All right, ladies and gentlemen, we are gearing up for part 3 of section 6.3. So section 6.3 is pretty heavy. There's a lot of terms, there's a lot of formulas, there's a lot of discussion about those binomial distributions. And now, of course, we're going to switch gears on you, classic AP statistics style, into geometric distributions. So binomial and geometric distributions are very similar to each other for just about one difference. Okay, there's one slight difference in the two distributions, but otherwise they're very similar to each other, and what we're going to do today is going to be very similar to what we did with binomials, but it's going to be just with one slight difference. All right, so here's the difference in a geometric setting. So a geometric setting arises when we perform independent trials, same as binomial, of the same chance process and record the number of trials it takes to get one success. There's your difference. On each trial, the probability P of a success must be the same. So here's what's the same. The same as binomial is the fact that the trials are independent, probability of one success. This is still success or failure. But here's what's different. What's different is the fact that we are going to record the number of trials it takes to get to one success. We're not giving a fixed number of trials. We're continuing the experiment until we get one success. So our number of trials is going to be different in every scenario. That's what happens. That's what they're saying down here in this box. So it says the number of trials that it takes to get a success in a geometric setting is the geometric random variable. The probability distribution of y, so they're calling this number y, is a geometric distribution when the probability P of a success on any trial. So you still have your probability P for success on any trial, but now your y variable is how long does it take you to get to one success. So let me give you an example. Let's say I'm working with a deck of cards. There's 52 cards in a deck, 4 of them are queens. So I say to you, choose 10 cards, one at a time, replacing the card after you've drawn it. Out of those 10 cards, record the number of queens that you select. That's a binomial distribution. I've got a fixed number of trials, 10 cards is what I'm going to pull. I have a probability for each one. 4 out of 52 is the number of queens. It's success or failure, queen or not, and each card is independent from the next. It's not changing anything from one to the next draw of the card. Okay, that's binomial. If I say to you instead, take a deck of cards, pull one card at a time, putting it back, keep selecting a card until you get a queen. Now that's geometric. It's not a fixed number of trials. It's continuing the process, repeating the process over and over until you get a until you get a queen. That's what makes it a geometric distribution. So the number of trials is not fixed. That's the slight difference, okay? So we call that variable y instead of variable x. Binomial was variable x. Now we're looking at variable y. So if y has a geometric distribution with probability P of success on each trial, the possible values of y are 1, 2, 3. You could get a success on the first draw. I could draw a queen the very first card. Or it could take me 30 cards to get a queen. You just don't know, you know? So if k is any one of these values, k is basically the number of trials it takes you to get to a success. Your probability looks like this. You've got the probability of failure raised to the number of failures, or raised to the number of trials minus 1. Then multiplying by the probability of success. And technically that probability of success is raised to the first power because it's your first success. But we all know that we don't need to raise something to the first power. It doesn't make a difference. So I've got the probability of failures raised to the number of failures times the probability of success. That is what the probability of that geometric variable will look like. All right, so let's take a look at an example. It says I think it's Local, I don't know. Mr. Local or Lachelle, Mr. Local's class, Lachelle's class, decides to play the Lucky Day game. A student will be selected at random from your class and asked to pick a day of the week, for example, Thursday. Then your teacher will use technology to randomly choose a day of the week as the lucky day. If the student picks the correct day, the class will have only one homework problem. If the student picks the wrong day, your teacher will select another student from the class at random and repeat the process. The game continues until a student correctly picks the lucky day. Let y equal the number of homework problems that the class receives. Find the probability that the class receives exactly 10 homework problems as a result of playing the lucky day game. So the first thing that we have to identify here is the fact that y, our variable, is a geometric distribution. So y is a geometric variable, or a geometric distribution, I guess you could say, with the probability, that's the other thing you have to identify, probability equaling 1 out of 7, because the probability that you get the lucky day is there's 7 days and only one of them is lucky, so that's 1 out of 7, okay? And what makes this, again, what makes this geometric is either success or failure, and you're going to keep playing the game until you win. You keep playing the game until you get the quote-unquote lucky day. All right, so then what we know is the probability that there is exactly 10 homework problems would look like this. So the probability of y equaling 10 is the probability of failure, or in other words, 1 minus the 1/7 raised to the 9 failures. Because if the 10th person is the success, that means that 9 people failed up until that 10th person. So 9 people failed, which means I need the probability of failure, or 1 minus the 1/7, times that 1 probability of success. And again, you can call that raised to the first power, but we know raising something to the first power doesn't really make a difference. I need to type this all into my calculator. I'm going to go ahead and call this 6/7, because if there's 1 successful day, then there's 6 losing days, and then times 1/7, and type all that in. Use parentheses, put parentheses around your fractions. So open a parenthesis, 6 divided by 7, close it, raise it to the 9th power, get out of that power, times, open a parenthesis, 1 divided by 7, and go from there, and I get a probability of 0.036, roughly. Okay, so there's my probability there. So now we're going to look at the same scenario, same example, but in part B, we're looking at the probability of y being less than 10. Probability of y being less than 10. So here's how this would work out. We would have to, in our calculator, for part B, this is what this probability looks like. We would have, this is like saying you get a success on the first try, a success on the second try, a success on the third try, a success on the fourth try, and so on and so forth. So if I add all those up all the way up to 10, or I guess I should say up to 9, because we're looking at less than 10, I would have this. I would have the probability that my success happens on the first try is just 1/7. Then I would need to add the probability that my success happens on the second try. So that means I have 1 failure times the 1 success. Then I'd have the probability that it's on the third try. So that's 2 failures times the 1 success. I need to keep that going. Plus, the probability that it's on the fourth try is 3 failures. So failure raised to the third power times the 1/7. Keep going. Keep that all the way up. The last one would be 8 failures. So 8 failures and 1 success. That would be on the 9th try. And I don't need to go to the 10th because I want to be strictly less than 10. I'm not including the 10th. So I would have to go through and type all of that into our calculator. Now, it's not really that big of a deal to go through and type all this into our calculator. However, going up to 10 isn't so bad. But what if this was y is less than 20? Now you get a whole lot more to type in, and that's just going to take a long time. So there's an alternative approach here. Or you can think of it this way. The probability that your variable is less than 10 is the same thing as 1 minus the probability that your variable is greater than or equal to 10. So basically what that means is it's 1 minus, not 1 over, sorry, 1 minus having 9 failures. If you get 9 failures, that means that you had no successes in your first 9 attempts. And that's what we're really looking at. We're looking at the first 9 attempts. So if you had 9 failures in your altogether in your first 9 attempts, and you take 1 minus that, that's the probability of getting at least 1 success. If you think back to chapter 5, we talked about the probability of at least in chapter 5. So this is like saying 1 minus the probability, or 1 minus the failures. So 6/7 to the 9th power. So that 6/7 to the 9th power is failing 9 times in a row. If 9 people fail in a row, that means you got no successes in those first 9 attempts. If you take 1 minus that, then you'll get at least 1 success in those first 9 attempts. So that makes it a little bit easier to calculate this probability. So if I type that into my calculator, this right here, 1 minus, open a parenthesis, 6 divided by 7, close your parenthesis and raise it to the 9th power, I end up with the 0.75, roughly 0.750 for my probability. Now, you can go through and type all of this in. It's not so bad when you're only typing in 9 combinations. You know, you've got 1, 2, 3, 4, and so on and so forth, all the way up to the 9th combination. But that's still quite a bit to type into your calculator at one time. And the more you type into your calculator at once, the more likely you are to make a mistake. So the other alternative is when you're doing less than, I can do 1 minus the greater than. And the greater than is saying I have everybody fail and then take 1 minus. Okay. And then even better than that is our fancy dancy machines. It's so nice to have a graphing calculator that will do all of these things for you. You just have to consider what your K value is, what the number of successes is, basically, or the number of trials it is to take you to get to a success. That's what I meant. So for this scenario, the first one's not so hard. You're going to do geometric PDF because you want the probability at exactly 10. So geometric PDF is when you're doing exactly 10. That's your equals. It's the CDF that's the cumulative. That's what that C stands for. So that's when you're getting into an inequality. When you get into an inequality, you're looking at CDF. Okay. So geometric PDF, go into that distribution menu, second vars, which is distribution. If you keep scrolling down, we found binomial PDF at options A and B. At least on my calculator, they're option A and B. Keep going. Keep going all the way to the bottom of that menu. The last 2 options are geometric PDF and geometric CDF. So I'm going to do geometric PDF just to test it out. And let's say that my probability is 1/7 and my X value is 10, meaning I want exactly 10 trials. Okay, I get a probability there of 0.0356, which is approximately what we got when we did it by hand. Now do this. This was like part A of that example. Now this is part B. Okay, so in part B, if I want X being less than 10, that means that my number of failures is 9. Okay, so let me say that again. If I want the probability to be less than 10, that means that my number of failures is 9. So 9 is what I have to type in there. So go back into second distribution. This time I'm going to use geometric CDF, which is the very last option. My probability is still 1/7 on each individual trial. And this time my X value is 9 because I have 9 failures before I get that 1 success. And there's that 0.750. Okay, so really, really nice to have this tool that will do things for us. Understanding the formula is still kind of important because you're going to see the formula on your AP exam. You don't have to have the formula memorized. This is a formula. These are 2 formulas that will be given to you on your formula sheet, but you still need to know what they mean. And that's sometimes harder than even just knowing what the formula is. All right, so then just one last little tip about geometric random variables. It says the table shows a histogram. The table and histogram show part of the probability distribution of Y, the number of picks it takes to get to match the lucky day. We can't show the entire distribution because the number of trials to get the first success could be a very large number. It's possible that you have to keep going and going and going and going and going. So they stopped it at 25, but we go until we get a success. So that could go on for a long time. So here's the probability distribution table. Now, notice the ellipsis here at the end. It's not possible to complete this table because, again, like we said, we don't know how long it would take us to get to the end. Now, your probability is going to drastically go down with each increasing trial. The likelihood that it takes you 50 trials to get one success is a lot lower than the likelihood it'll take you 5 trials, okay? So notice that you start with a probability of 0.143, then 122, then 105, then 0.9, and it's steadily decreasing as you continue. So your histogram here, as we would expect, is skewed to the right. And that's going to be the case for geometric distributions pretty much in general, because you can never finish. It's going to be like a limit. If any of you took pre-calculus, it's like a limit. You can never get down to 0. You're never going to finish off the probability distribution, but you're going to get closer and closer and closer to 0 with each increasing trial. So your distribution is always going to be skewed to the right. So the mean, here's our mean and our standard deviation. Well, just our mean, sorry. The mean, or in other words, the expected value of a geometric random variable is a very easy equation. It's 1 divided by whatever your probability is. That's it. 1 divided by your probability. So if you have a geometric random variable, the mean, or in other words, the expected value is 1 over p. All right, so that's a little brief introduction to geometric random variables. Hopefully you can kind of see the difference between a geometric and a binomial. And yeah, looking at yet another formula and yet some more calculations and yet some more tools in your graphing calculator that are going to be really helpful for you. So thanks for tuning in. This is the last part of section 6.3 and the last lesson of chapter 6. So we'll move on with wrapping up the chapter from here. I will catch you next time.